Okay guys, let's go over the review. So the first question just asks you to write down the two limit definitions of the derivative. You have to know these formulas. The first limit definition is f prime of c equals the limit as x approaches c, f of x minus f of c over x minus c. And the second limit definition is f prime of c equals the limit as h approaches 0 of f of c plus h minus f of c all over h. Number 2, consider the function f of x equals x squared. Prove that f prime of x equals 2x using the second limit definition of the derivative, not the power rule. So here f of x equals x squared. So if I use the second limit definition, in this case, I'm looking for the derivative of the function not at a particular point like 5 or 6 or 7. I'm looking for the derivative in general. So I'm not looking for the derivative at a particular point like 5 or 6. I'm looking for the derivative at x. That means instead of replacing c with a number like 5 or 6 in this formula, in the second limit definition, I replace c with x. So f prime of x, that is the derivative in general, is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So what is that in this case? That would be the limit as h approaches 0 of, well, what is f of x plus h? Well, that means you walk over to your function, which is right here, x squared, or it's right here, and you replace any x that you see with x plus h. That will give me x plus h quantity squared minus x squared, right? That's f of x right here, all over h. So this is now just sort of a limit, and I have to evaluate it. If you replace h with 0 right now, you'll get 0 over 0, which means you need to simplify. So that would be the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h, which is the limit as h approaches 0. Well, the x squareds cancel, so I get 2xh plus h squared all over h. You can factor a common factor of h out from the numerator, like this. The h's cancel, and then you're just left with the limit as h approaches 0 of 2x plus h. And if you replace h with 0 now, you just get 2x plus 0, which is just 2x. And that is, of course, the derivative. Most of the time when we use this limit definition of the derivative, you're looking for the derivative at a particular location. But here, I didn't ask for f prime at a particular value. I asked for f prime in general. That's why c was x rather than a particular number. This is, of course, like a manual proof that the derivative of x squared is 2x without using the power rule. Number 3, find the values of each limit below. You're welcome to try evaluating the limits algebraically, but there's an easier way. Yeah, you really should not try to evaluate these algebraically. That's a mistake. If you see a limit in this unit, it's a derivative of some kind. The idea with each of these is that each of these limits is actually just the derivative of some function at some point, right? And you're supposed to recognize that and then use derivative rules to find the value of the limit. So this guy right here looks a lot like the second limit definition of the derivative, doesn't it? And if you compare them, it looks an awful lot like the function in question, f of x, is sine of x, and the value of c, the point at which the derivative is being found, is pi over 4, right? Compare this expression with this one, and I think you can tell that c is pi over 4, and the function f is sine of x, right? So in other words, this limit right here is exactly what you would get if you applied the second limit definition, this formula right here, to this function at this point. You might wonder, what's the root 2 over 2? Well, that's exactly f of c, like that's sine of pi over 4. That's root 2 over 2. So it matches perfectly. So once you recognize that this expression here is just this formula applied to this function at this point, and you say, oh, well, this formula represents something. It represents the derivative of sine of x at pi over 4. You say to yourself, well, I know what the derivative of sine of x at pi over 4 is, right? I mean, the derivative of sine of x in general is cosine x. Therefore, the derivative at pi over 4 specifically is just cosine pi over 4, which is square root of 2 over 2. Okay? So that's part A. Part B, very similar. You should compare this expression right here with the first limit definition. It looks a lot like that, doesn't it? And if you compare this expression here, if you compare the first limit definition of the derivative to this expression, you can tell that c is 16, and the function f of x is fourth root of x. That tells you that this limit right here is what you would get if you applied this formula to the function f of x equals fourth root of x, which is x to the 1/4, at the point c equals 16. So, okay, this limit is representing something, right? It represents the derivative of this function at this point. So I can find that just using the power rule. F prime of x would be 1/4 x to the negative 3/4, and then f prime of 16 would be 1/4 16 raised to the power of negative 3/4. That's 1/4 times 1 over 16 to the positive 3/4. That's 1 over 4 times, well, this is kind of an interesting number because we told you not to use your calculator throughout this review. 16 to the 3/4 can be interpreted in a couple of different ways. Probably you're accustomed to thinking of it as meaning the fourth root of 16 to the third. And so maybe you say to yourself, oh my god, I've got to cube 16, and then I've got to find the fourth root of that number. How am I going to do that without a calculator? Well, actually, there's an alternative way of interpreting this. The thing is, you can cube and take the fourth root in either order. Like, you can take the fourth root first, then cube. And arithmetically, it's much easier to do that, right? So instead, just start by taking the fourth root of 16. What's the fourth root of 16? You probably don't have it memorized, but like pretty quickly you're going to figure it out. It's 2, right? 2 to the 4th is 16. So if you take the fourth root first, that's just 2, and then you're cubing that. Okay, that's just going to give you 1 over 8, right? So 1 over 8 equals 1 over 32. Yeah, so each of these guys in number 3 is really a derivative in disguise. Each of these limits represents the derivative of some function at some point. And to evaluate these limits, you are not performing complicated algebraic manipulations like we were in Unit 1. Instead, you are just recognizing the fact that these limits represent the derivative of some function at some point, and then you're saying, oh, well, I know what the derivative of that function at that point is, and you compute the limit that way. These guys are tough. These geometry problems, these are tough, definitely. Number 4, the line y equals 4x plus 11 is tangent to the function f of x equals x squared plus k at some point c. Find c, then find the value of k. That is interesting. So the key idea here is that this is the equation of the tangent line at some mystery point C. That's the only thing we know about this point C. And so that is the piece of information we have to use to find C. How can I use this to find c? Well, the idea here is this is the equation of the tangent line at c. Now, if you stare at this equation, it's in slope-intercept form, right? That's y equals mx plus b form. And so it's very clear that the slope of this line is 4. Okay, the slope of this line is 4. But again, what line is that? It is not just any line, it is the tangent line at c. So the slope of the tangent line at c is 4, right? The slope of the tangent line at c is 4. Which means that the derivative of f of x at c is 4. In other words, we can find c by asking when is the derivative of this function equal to 4, right? C is the very location at which the derivative of this guy is 4. So to figure out where that occurs, I take the derivative and I set it equal to 4, and then I solve. So the derivative of f of x is just 2x because k is a constant, its derivative is 0. So I find 2x is equal to 4, which means x is equal to 2. That's c, right? Or at least that's the x-coordinate of c, right? That's the x-coordinate of c. Because, yeah, so now how do I find k, right? How do I find k? Well, the idea here is that this equation here and this function here, well, these are actually two functions, right? This is a function, and this is also a function. And the key insight is that these two functions have the same value at 2. They have the same value at c. Like, if you think about the graph of the function and the tangent line, for example, if you look at the picture in number 5, of course it's a different problem, different function, but it doesn't matter. The picture serves the purpose that I'm trying to argue for here. At this point, like, this point is on both the tangent line and the curve, right? The value of the linear function and the value of the quadratic function are the same at this point, okay? Because that point is on both graphs. And the same is true here, right? So basically, I know that this function here and this function here have the same value at 2. So that means, well, what is the value of this function at 2? Well, it's 4 times 2 plus 11, which is 19. That means that the quadratic function, f of 2, must also be equal to 19, which tells you that 2 squared plus k is equal to 19, which tells me that k is equal to 15. Okay, cool. Hard question. Number 5. Shown below is the graph of the function, blah, blah, blah. Also shown is the tangent line to the graph at x equals 1. The tangent line has equation, blah, blah, blah. Find the values of a and b. Okay. There's a couple of things that I can say here. Again, just like in number 4, one thing that you can notice is this point is on both graphs. It's on the graph of the tangent line, and it's on the graph of this quadratic function, right? And so, well, actually, maybe that's not super important just yet. What I can say is, hey, look, this point right here is on the graph of the quadratic function. That means that if I plug 1 in for x in this quadratic function, I should get -4. So let's just do that. That's telling me f of 1 is -4. So in other words, a times 1 squared plus b times 1 plus 1 should be equal to -4. In other words, a plus b plus 1 is -4. In other words, finally, a plus b is equal to -5. that is an equation involving a and b, and that's great. But of course, I have two unknowns, which means I need a second equation, right? I need a second equation. Where's that other equation going to come from? Well, I haven't really used this yet, have I? Right? Like, I haven't used that equation at all. What that equation is telling me, look, this is the equation of this line. And that line is a special line. It's the tangent line at x equals 1. This line, very much like in number 4, this line right here, that equation is in slope-intercept form, like y equals mx plus b form. So I can tell that the slope of this line is -2. So the slope of this line is -2, and which line is this? It's the tangent line at 1. So I can say the slope of the tangent line at 1 is -2. But that just means that the derivative of the quadratic function at 1 is -2. So that just means f prime of 1 is -2. That's going to give you a second equation involving a and b. F prime of x in general is 2ax plus b, which means that f prime of 1 is 2a times 1 plus b, and that's supposed to be equal to -2, so I find that 2a plus b is -2. That's my second equation. So equation number 1, equation number 2, now you have a system of equations with two unknowns, and you can solve. How do you solve? I like substitution. You can use elimination, whatever. I'll solve that equation for b, maybe. I find b is equal to -2 minus 2a, and then I'll substitute that into this equation, replace this b right here with -2 minus 2a. I find a plus -2 minus 2a is equal to -5, and then a minus 2 minus 2a is equal to -5. So negative a is equal to -3, I think. So a is equal to 3. And then if I substitute that back into that right there, I find b is -2 minus 2 times 3. That's -2 minus 6, so -8. Let me check the answer on that real quick, because there's a lot of steps in that, and I did it kind of fast. That was number 5, right? It says a is 3, b is -8. Cool, we're good. Okay, lovely. Moving on. Okay, so those are the hard problems, right? Number 6, shown below is the graph of some function f of x. Evaluate each expression. Many do not exist. Note all the primes. Okay, limit as x approaches -1 from the left, f prime of x. So I'm asking, what is the derivative doing as you approach -1 from the left? Well, if I approach -1 from the left, it looks like the slope is just constantly -2. So I'd say it's -2. Same thing, but from the right. If I approach from the right, the slope is just constantly -2. So I would say, again, this is -2. F prime of -1. Well, I can tell you that does not exist, okay? Because the original function has a discontinuity at -1, which means the derivative is undefined at that location. I haven't drawn the derivative graph yet, but I can tell you that if I did, the derivative graph would have a removable, like a hole, discontinuity at -1, because the derivative is approaching the same thing from both sides. It's approaching -2 from both sides, but at -1, the derivative is undefined. That's a hole. D, limit as x approaches 0 from the left, f prime. I think, again, you approach from the left. I think the slope is still just constantly -2, so I think that's -2. 0 from the right. I don't really know. I mean, it's curvy, right? As I get close to 0 from the right, that slope looks like, I don't know, maybe it's a third or something, like 1/3 maybe. So maybe about 1/3. I think you're supposed to approximate it. F prime of 0, well, right away I can say f prime of 0 does not exist because there is a corner at that location. I haven't drawn the derivative graph, but if I did, I would know that there is a jump discontinuity at this location because the derivative, if you look at the derivative approaching from the left, it's -2, but if you look at the derivative approaching from the right, it's positive 1/3. So, the left and right hand limits are two different values for the derivative, which means the derivative graph would have a jump discontinuity at that location. G, limit as x approaches 2 from the left. F prime, I think that's infinity, right? Like as you get, this is a vertical tangent line here. As you get closer and closer to 2 from the left, that slope is getting closer and closer to positive infinity, right? So yeah, so I'd say that's positive infinity. From the right, what is the slope doing? Well, as I get closer and closer, again, the tangent line is getting more and more vertical. I think it's also going to positive infinity. And then f prime of 2, undefined because it's a vertical tangent line. If I think about the graph of the derivative function, though, the derivative function, I think, would have a vertical asymptote here too, right? Because the slope is approaching infinity from both sides. On the same grid, sketch the derivative of f prime. We can quickly look at the answer. For number 7, here it is. It's just what I said, right? The slope along this portion is constantly -2, so there it is, constantly -2, but of course it's undefined at -1, right? So you got that hole there. And then here, like I said, at 0, there's a jump discontinuity in the derivative graph, because f prime, if you look at f prime from the left, you're getting -2, but if you look at f prime from the right, you're getting something else, maybe 1/3, right? So there's a jump there, and then vertical asymptote, just like I said. Okay, moving on. Around to number 7. Number 7, we are taking derivatives. So 7a. Find derivatives of the following functions, blah, 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 blah. Okay, yeah. Okay, by the way, use clear notation indicating when you are rewriting y and when you are rewriting y prime. People get super sloppy about this. I'll say what I mean as I go along. Okay, so 7a. Do I need to rewrite this? No, it's ready to go. This is just y prime is 2 cosine x. Derivative of cosine is negative sine, so that second term is going to be -3 sine x. Cool. 7b. I would rewrite that as 1/5 cosine x, right? Notice that's y, right? I haven't taken the derivative yet. I just rewrote it, so that's y. I'm calling it y. But in the next step, I'm going to take the derivative. That's why it gets a y prime. So that's going to be -1/5 sine x. 7c. Do I need to rewrite this? No, it looks good. I think it's ready for the power rule. So y prime is going to be, well, the 3 comes down and cancels the 3 in that denominator. You're going to get 2x squared minus 8x minus 12. And then, of course, derivative of 9 is 0. Great. 7d. This guy. Do I need to rewrite this guy? No. It's ready for the power rule. So y prime is -12x to the -4, right? Subtracting 1 there. So -12x to the -4 plus 1x to the -1/2. Okay, let me rewrite this without negative or fractional exponents. That would be -12 over x to the 4, right? This negative exponent does not affect the 12. The 12 remains in the numerator. Plus 1 over x to the 1/2, but of course x to the 1/2 is the square root of x. Okay? E. Yeah. 7 to the 28th. I mean, hopefully you don't say that that's 28/7 to the 27th. That's wrong, right? This is a constant. It's a constant. Derivative is 0, right? You shouldn't be using the power rule. There's no x. 7f. I would rewrite that first. So that's y equals 1/3 x to the 3rd plus 1/3 x to the -3rd, right? Again, that second term is not 3x to the negative 3. A lot of people think it is. It's not. Okay, the coefficient is 1/3 there. So that's rewriting the original function. Now I'm ready to take the derivative. I get x squared minus x to the negative 4. Right? Again, notice, when I rewrite the original function, I'm calling that y. Only when I actually take the derivative is that y prime. Okay, so, and now I'm going to rewrite the derivative, so that's this guy right here. 7g. Okay, this obviously needs to be rewritten. That's y equals x to the 1/2 plus x to the 1/3. And then I would say that's x to the negative 1/4. So that's y rewritten. Now I'm going to take the derivative. It's 1/2 x to the negative 1/2 plus 1/3 x to the negative 2/3 minus 1/4 x to the negative 5/4. And so now I'm going to rewrite that, I think. That's 1 over 2x to the 1/2 plus 1 over 3x to the 2/3. Oops. Minus 1/4 x to the 5/4. And if we don't like the fractional exponents, we could say that's 1 over 2 square root of x plus 1 over 3 third root of x squared minus 1 over 4 times the 4th root of x to the 5th. 7h, you need to rewrite that before you can use the power rule. You need to expand that out. That means 2x plus 3 times 2x plus 3, right? It does not just mean square each term separately, right? It's not just like 4x squared plus 9. That's wrong, okay? That means 2x plus 3 times 2x plus 3, which means multiplying out, I get 4x squared plus, I think you're going to get 12x, right? Because 2x times 3 is 6x, you double that, plus 9, which means y prime, now I'm ready to take the derivative, is 8x plus 12. Cool. 7i. For that guy, you need to rewrite. You need to split that fraction. Do not take the derivative of the top and the bottom. It doesn't work that way. That's x cubed over x minus 2 over x. Right, so I split the fraction. I think I still need to rewrite this. That first term simplifies to x squared. That second term simplifies to minus 2x to the negative 1. Now I'm ready to take the derivative. Y prime is 2x plus 2x to the negative 2. That means y prime is 2x minus 2 over x squared. Number 8. Consider the function f of x equals 2 cosine x. Write the equation of the tangent line to f at x equals pi over 6. This is showing that you guys need to know your trig values, right? So, equation of the tangent line. The first thing I do is I write down y minus y1 equals m times x minus x1. Okay, I always just write down the point slope form. All right, so that tells me that I need two things. I need the point, which is my x1 and my y1, and I need the slope of the line. That's your m. So let's start with the point. Well, to find, I'm thinking about the tangent line at x equals pi over 6. So the point on the line has x coordinate pi over 6. To find the y coordinate, I plug pi over 6 into this original function, right? So what would that be? F of pi over 6, that would be 2 cosine pi over 6, which is 2 times square root of 3 over 2, which is just square root of 3. Okay, so that is the y coordinate of the point. So my point is pi over 6 comma square root 3. For the slope, I need to take the derivative. F prime of x is negative 2 sine x. The slope, of course, is not this guy. Slope is a number, right? I need to evaluate this guy at pi over 6. So that's negative 2 sine pi over 6, which is negative 2. Sine pi over 6 is 1/2. So that's negative 1. So I say the equation of the tangent line is y minus y1, which we said was root 3, equals m, which is negative 1, times x minus x1, which is, of course, pi over 6. Okay, so that's my equation. Number 9. Find the equation of the tangent line at the curve x equals 3. Same thing, I start by writing down y minus y1 equals x times x minus x1. For the point on the line, well, the x-coordinate of the point is 3. To find the y-coordinate, I plug 3 into the original function. So let me see what that is. F of 3, that's going to be 2/3 times 3 cubed minus 4 times 3 plus 1. So that means f of 3 is 2/3 times 27 minus 12 plus 1. So f of 3 is, the 3 divides into the 27, giving you a 9. So it's 2 times 9. So that first term is just 18. Minus 12 plus 1. So that's 7. Okay, so that's the y-coordinate of the point. For the slope, I need to find the derivative. So f prime of x is 2x squared minus 4. Of course, that's not your m, right? M is a number. That's not a number. To find m, you need to evaluate this at 3. So that's 2 times 3 squared minus 4. That's 2 times 9, 18 minus 4, so that's 14. So I say the equation of the tangent line is y minus 7 equals 14 times x minus x1, which was just 3. 9b, find all points on the curve where the tangent line has slope 1/2, show your work. Well, if the tangent line has slope 1/2, that just means the derivative is equal to 1/2. So the question is asking you, where is the derivative equal to 1/2? So you're going to take the derivative, which is 2x squared minus 4, and you're going to set that equal to 1/2 and solve for x. So 2x squared equals 1/2 plus 4. That's 9 halves, right? I think. And then divide by 2, I get 9/4. Take the square root, I get x is equal to, do not forget your plus or minus. You will lose points if you forget about that. Square root of 9 over 4. Taking the square root of a fraction just means taking the square root of the top and the bottom, so that's plus or minus 3 over 2. Okay? If you wanted to find the y-coordinates of these points, you could plug them into the original function, but I don't really feel like doing that because fractions. Yeah. 9, and I don't think I need to. 11, don't know why there's no number 10, but who cares? Determine the coordinates of the points at which the graph of the function blah 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 has a horizontal tangent line. Oh, okay, they want both coordinates here. Okay, you don't have to shout. Okay, so the graph having a horizontal tangent line just means the slope of the tangent line is 0. So really the question is asking, when is the slope of the tangent line 0? In other words, when is the derivative 0? So I'm going to take the derivative and set it equal to 0. Of course, to find the derivative, I have to rewrite this function. This is x to the negative 1 minus x to the negative 2. F prime of x would be negative x to the negative 2 plus 2x to the negative 3. If I rewrite that, that's negative 1 over x squared plus 2 over x cubed. And what am I doing with this? I want to know, when is this thing equal to 0? Okay, how do you solve this equation? Well, one way that you could solve it would be to move, for example, this term over to the other side, and then you'd get 2 over x cubed is equal to 1 over x squared, and then you could cross multiply, right? If that makes sense to you. Alternatively, you could say, oh, the problem here is I've got variables in my denominators, and the way to resolve that is to clear denominators. Multiply both sides of the equation by whatever you need to get rid of the denominators. In this case, if I multiply everything by x cubed, that'll get rid of all the denominators. So like multiply this guy by x cubed, right? So -1, let me just write it. -1 over x squared times x cubed plus 2 over x cubed times x cubed equals 0 times x cubed. Well, okay, so that first term is going to be -x. That second term is just going to be 2, and the right-hand side, 0 times x cubed is, of course, just 0, right? So you find 2 is equal to x. Yeah, okay, so I think x is equal to 2. They want the y coordinate. How do I get the y coordinate? Well, you just plug 2 into the original function, so that's 1/2 minus 1/4, which is 1/4, right? So I think the coordinates of the point are 2, 1/4. Number 12, given this function, blah, 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 if f prime of 2 is 3, what is the value of b? First of all, that is a horrendous way of writing that function. Right away, I can tell there's a better way of writing that. You could split well, there's a couple ways of doing it. I guess one way of doing it is to split the fraction, like split the big fraction, right? I've got one thing minus a thing, all divided by x. I can distribute that division by x, so I get x over x minus b over x, right? I'm splitting that fraction. Okay, obviously that first term is 1. Nobody's going to have any trouble figuring that out. That second term's a little bit weirder, though. Like, how do you simplify this? Look, I strongly recommend that whenever you have fractions within fractions, you need to get it in the form of one fraction divided by another fraction. And that's not quite what I have. I have one fraction divided by x, all right? I want to view that x as being a fraction. So how do I turn it into a fraction? Well, I make it over 1. Okay, now it's one fraction divided by another fraction. And now it's very clear, keep it, change it, flip it, multiply by the reciprocal. However you see it, you get b over x times 1 over x. If you thought that those x's were going to cancel, they do not. They do not cancel. You find the function, therefore, is equal to 1 minus b over x squared. And remember, I'm trying to find the derivative of this thing, so I need to still rewrite it more. This is 1 minus bx to the -2. Okay, finally I can take the derivative, right? So f prime of x is going to be, derivative of 1 is 0. Derivative of that second term is positive 2bx to the -3, which is 2b over x cubed. Okie dokie. So that's the derivative. And we're told that f prime of 2 is equal to 3. Well, that means that if I plug 2 in for x, I should get 3, right? So f prime of 2 is 2b over 2 cubed, and that's supposed to be equal to 3. That's an equation which I can solve for b. So that denominator is 8. So multiply both sides by 8, I get 2b is equal to 24, which tells me b is equal to 12. Number 13, find an equation for the line tangent to the curve, I mean, we've done this many times. You want to do y minus y1 equals m times x minus x1. So you need your point and you need your slope. The point, well, the x-coordinate is, of course, -2. To find the y-coordinate, you plug -2 into the original function. So that's this guy. So what is that? That's 5 times 4 is 20. -2 to the 4 is 2, 4, 8, 60. That's positive 16, and then times another negative 2 is negative 32, I think. So that's negative 12. So I think the y-coordinate's negative 12. I'm doing these quickly. I hope I'm not doing dumb arithmetic mistakes. For the slope, we take the derivative, right? So that's going to be 10x minus 8x. Oh, did I forget a 6? Yeah, I didn't see the 6 here, did I? Okay, so right, so I did make a mistake. So that's plus 6, right? So plus 6. So that would be not negative 12, but negative 6. Okay, good. Phew. So the slope, the derivative, yes, is 10x minus 8x cubed, right? 10x minus 8x cubed. Okay, so I need to evaluate that at negative 2. So that's 10 times negative 2 minus 8 times negative 2 cubed, which is negative 20 minus 8 times negative 2 cubed is negative 8, right? So that's negative 20 plus 64, so 44. So I think the slope is 44. Again, I'm doing these super fast, and I tend to make mistakes when I'm typing mathematics as opposed to writing it, and also like talking out loud, explaining it while I'm doing it. So hopefully I haven't done anything stupid. Okay, so the y-coordinate's negative 6, so y minus negative 6, that's y plus 6, equals m, which is 44, times x minus negative 2, which is x plus 2. I'm going to go ahead and check that answer. I feel like I did that so fast. Yeah, that's right. Okay, cool, good. Number 14. Determine whether if each function below is differentiable, the indicated value of x. Use proper limit notation. Show all work clearly. Okay, fine. Okay. So I need to check two things. First of all, I need to check is the value of the original function, is the value of these two original functions the same at 2, right? And then I need to make sure that the derivatives of those two functions are the same at 2. So using limit, what I'm really saying here, technically I'm saying, okay, first of all, the function needs to be continuous at 2, which means the limit as x approaches 2 from the left needs to be equal to the limit as x approaches 2 from the right, which and all that needs to be equal to the value at 2. So what is this stuff? Well, limit as x approaches 2 from the left would be obtained by plugging 2 into that first formula. So that would be 4 times 2 squared plus 2 times 2 plus 1. Okay, and we want to know, is that equal to the right-hand limit, which would be obtained by plugging 2 into the second formula? That would be 2 cubed plus 6 times 2 plus 2. And is that equal to the value of the function at 2? Value of the function at 2 is just this guy again, right? It's the same thing. I'd be using the first formula, so I'll just copy and paste that. So are all these things the same? So that's 16 plus 4 plus 1. And then this guy here, that's 8 plus 12 plus 2. Are those equal? The left-hand side is 21, and the right-hand side is 22. Is that right? Did I mess that up somewhere? Because if those aren't equal, I can stop right there and say it's not differentiable, because it's not even continuous. You know what I mean? It needs to be. Let me just, instead of looking over my arithmetic, let me just make sure that that's, yeah. Right, no, that's right. Yeah, so it's not even differentiable. It's not even continuous at that point. Cool, so we can just stop, right? You don't have to worry about checking that the derivatives match. 14b, okay, so again, first I need to check continuity, so I need to ask, is the limit as x approaches 8 from the left equal to the limit as x approaches 8 from the right? And is that in turn equal to the value of the function at 8? Well, let's see. So the left-hand limit would be obtained by plugging 8 into the first function. So that'd be 3 times 8 to the power of 2/3 plus 8. Is that equal to the right-hand limit? Right-hand limit would be obtained by plugging 8 into the second function. That's negative 1/2 times 8 squared plus 9 times 8 minus 20. The value of the function at 8 is just this guy again, so like I'm not going to bother copying it. What is that? That is, so what is 8 to the 2/3? You can think of it as square 8, then take the cube root, or you can think of it as take the cube root, then square. You'll get the same answer. I would rather take the cube root first. Cube root of 8 is 2, and then 2 squared is 4. Or you could square 8, get 64, and take the cube root of that, which is also 4. Okay, is that equal to this guy here? That's negative 1/2 times 64, so that's negative 32. 9 times 8 is 72 minus 20. So that's 12 plus 8 is 20. And is the right-hand side also 20? Negative 32 plus 72, that's 40 minus 20 is also 20. Okay, so the function is continuous, right? The values of the original functions match at 8, but to be differentiable, the derivatives also have to match, the slopes have to match. So I've got to take the derivative of these two functions. Derivative of this first guy here is 2x to the negative 1/3, right? Yeah. And that's it, right? And the derivative of the other function is negative x plus 9. Okay, now the question is, are these two functions equal at x equals 8, right? It's not like, are those two functions equal as functions? It's, do they have the same value at 8? So the question is 2 times 8 to the negative 1/3, is that equal to negative 8 plus 9? What is this guy on the left-hand side? That's 2 over 8 to the 1/3. But 8 to the 1/3 just means cube root of 8, which is 2. So left-hand side is 2 over 2. The right-hand side is a 1. Oh, and yeah, so both sides are 1. So it looks like, yes, it's differentiable. 15. Find all possible values of a and b that would make the function shown to the right differentiable for all x. The only place where it might not be differentiable is the boundary point at 0. So we're going to be thinking about 0, right? So in order to be, it needs to be, of course, continuous at 0, which means the left-hand limit should match the right-hand limit should match the value at 0. So what is this telling us? The left-hand limit is obtained by plugging 0 into that first function. That's a times cosine 0. Cosine 0 is 1, so that's just a. Plus 14 times 0 is 0, so we'll forget about that term, and then plus 5. The right-hand limit, you'd plug 0 into the second function. That's 0 squared plus ab times 0 plus, I think you just get b, right, for the second guy. F of 0, this third thing, is just going to be the same as the first thing, so I'm not going to bother writing it. So we get one equation, right? We find a plus 5 is equal to b. The second equation is going to be obtained by saying the derivatives also need to match at x equals 0. So I'm going to take the derivative of each of these functions. Derivative of a cosine x is negative a sine x. Derivative of 14x is 14, and then that's it, because the derivative of 5 is 0. The derivative of the second function is 2x plus ab. The derivative of b is 0, because it's a constant. And then those two functions need to be equal specifically at x equals 0. Do not set these two things equal to each other. They're not supposed to be. They're just supposed to have the same value at 0. So negative a sine of 0 plus 14 needs to be equal to 2 times 0 plus ab. Sine of 0 is 0, so that first term vanishes. You find 14 equals, well, actually just 14 is equal to ab, right? This is now a system of equations that you need to solve. If you are accustomed to using elimination Elimination does not work on this system. You have to use substitution, which means get one of the variables by itself and then plug into the other equation. Fortunately, this equation already has the b by itself, so I'll use that. So I'm going to go to this equation and replace the b with a plus 5, right? Okay, now how do I solve this equation for a? Maybe you could just guess the solution to this one, you know what I mean? Product of two numbers is 14, but the thing is, it's a quadratic, and you should solve it the proper way, which is, distribute everything and then put everything on one side, so you get 0 equals a squared plus 5a minus 14. So you're looking for a pair of numbers that multiply to negative 14 and add up to 5. That would be 7 and negative 2, so a plus 7 times a minus 2. So that tells me a is equal to negative 7, or a is equal to positive 2, right? So I get two solutions for a, which means, of course, that I'm going to get two solutions for b when I go back to this equation, right? So if a is equal to negative 7, then b will be obtained, from this. B is going to be a plus 5, so negative 7. Negative 7 plus 5, that's negative 2. So one solution is a is negative 7, b is negative 2. The other solution, if I take a to be 2, then b will be, a plus 5. So that's 2 plus 5, which is positive 7. So these are the two values for a and b that work. Okay, 16, shown in each graph below is the graph of some fun. Sketch a graph of the derivative. I mean, what I would say here is basically, what I would say is that I probably want to save this as a PDF real quick so that I can draw on it. We're going to get to see the Macintosh's default graphing program, which is just one of the absolute worst things that you can imagine in software that's ever been designed. But anyway, whatever. How's that looking? That's pretty good. Okay, so I'm going to graph the derivative. I just look point by point. Like right here, the slope is very negative, so I'm going to make like a dot way down here, right? I go a little bit further along, the slope is less negative. I keep going, the slope is 0. I'm going to put a dot at 0, okay? I go along a little bit further, the slope is positive, maybe it's positive 1, maybe it's positive 2, whatever, put a dot here. I go a little bit further along, the slope is 0, so I make a dot at 0. I go a little bit further along, the slope is negative, so I make a dot negative. Okay, it looks like it's something like that, whatever. Okay, so it's some kind of parabola, stop that. Why are you correcting my curves? Okay. This guy here is a little bit weirder. Obviously, the derivative is 0 right here, so I'll put a dot right here at 0. If I go a little bit further, like right here, looks like the derivative is maybe negative 1, so put a dot at like negative 1. If I go further, then the derivative is like negative 2, negative 3. Okay, if I keep going, it looks like the slope gets more and more and more negative. Like right here, the slope is super negative, like negative 10, negative 100. I think there's a vertical asymptote here, right? So I think it's going to negative infinity there. And then I think, so if I go over here, like if I look right here, I think the slope is positive 1, so put a dot at positive 1. If I go a little bit further, the slope is like a big positive number, positive 2, positive 3, whatever. If I get real close, it's getting super positive. I think the slope is going to infinity here. You have another vertical asymptote there. So I would say, that's pretty good. Vertical asymptote, and the derivative graph looks like this. Yeah, okay, cool. Moving along. I mean, we did it in class. Look, the slope is constantly negative 2 along this portion, so constantly negative 2 along that portion. But then right here there's a corner, so the derivative needs to be undefined, so you want to use an empty circle there. Empty circle. And then all of a sudden the derivative jumps to positive 2, and it's kind of constantly positive 2 all along this portion. So the slope is just constantly positive 2 all along that portion. At some point or another, it starts to kind of curve, right? Like the slope is decreasing, and here it reaches 0. So my curve is going to something like that, reaches 0. And then I don't know why the program automatically puts like arrows on things sometimes. Just ignore that. The slope is 0 all along here. The slope is 0 all along here. Cool, cool. Then you get to this point, the original graph has a discontinuity, which means the derivative graph is undefined at that location. So that should be an empty circle at 3. And then the graph, the slope continues to be 0, so slope continues to be 0. Then the slope starts to decrease, like it's getting negative, right? It's getting negative. And then as I get closer and closer to here, you know, the slope is getting more and more and more negative. I think it's like negative 10, negative 100. So the derivative graph has a vertical asymptote at that location. So vertical asymptote. And then after that, the slope, you know, there's a corner here, so the derivative is undefined at 8. But afterwards, the slope is just sort of constantly negative 1. So it's undefined at 8, but then after that, the slope is just constantly negative 1. Cool. Okay. So now we are moving on to AP multiple choice questions. Cool. So this is AP 7. Let f of x be what is the instantaneous rate of change? That just means what's the derivative at 3. That's all that means. So derivative is 3x squared minus 12x plus 8. F prime of 3 is 3 times 3 squared minus 12 times 3 plus 8. So that would be 27 minus 36 plus 8. That is 27 minus 30. Why can't I do that in my head? I mean, 36 minus that's negative 9, isn't it? Negative 9 plus 8, right? I think that's negative 9. 20. Yeah, it's negative 9. I don't know why I'm having such a negative 9 plus 8. Negative 9 plus 8. There we go. So I think that's negative 1. Is that one of the... Okay, good. Looks like it's C. Okay. 20... Which of the following of these things is true about f? Does the two-sided limit exist? Well, let me think. If I approach from the left, I'm going to get 3 plus 2 is 5. I approach from the right, I'm going to get 3 times 4, which is 12, minus 7, which is also 5. So 1 is true because you get the same thing from both sides. Is it continuous at 3? Yeah, well, the only thing you need beyond the two-sided limit existing is the value of the function, like f of 3 also exists and is also equal to 5, and it is, right? Like there's that little underline there, so f of 3 is also 5. So everybody matches up, so 2 is also true. Is it differentiable? Well, you gotta check the slopes. The slope on the left, well, the derivative is just constantly 1, so the slope is definitely just 1 at 3. In fact, it's sort of like, you know, it's always 1 on the left. But the slope is 4 on the right, right? So the slopes don't match. So 3 is false, right? So it's just 1 and 2. So 1 and 2 only, that would be choice D, okay? 14, let f of x be the function. What are the values of a and b for which this function is differentiable at 1? Okay, so first of all, the original functions have to agree at 1. So 1 plus b has to be equal to a times 1 squared. So 1 plus b needs to be equal to a. That's one equation. Second equation comes from the fact that the derivatives, like the slopes, need to match at x equals 1. The derivative of the first function is just constantly 1. There's not even an x there. The derivative of the second function is 2ax. Of course, again, it's not that 1 equals 2ax. It's that, you know, these things need to be equal specifically when x is 1. So I do that, right? Which is going to tell me that a is equal to 1/2. And then plugging back into this guy tells me that 1 plus b equals 1/2. So I think that b is negative 1/2. Yeah, looks like choice is A. 18, an equation of the line tangent of the graph blah, blah, blah is, okay, tangent line equation. What do you do? Oh, this is AP 18. So yeah, so I need y minus y1 equals m times x minus x1. Okay, so what is my point? Oh, I know what the point is. It's 0, 1. They gave you the y-coordinate here. You actually don't, they could have just told you at x equals 0, and you could find the y-coordinate for yourself, but whatever. So 0, 1, cool. So I already know the point. It's 0, 1. That's great. I just need to know the slope, okay, so which means I need to find the derivative. So y prime is 1 minus sine of x. So what is y prime evaluated at x equals 0? That's 1 minus sine 0. Sine of 0 is 0, so that's just 1. So the slope is 1. So I think it's y minus y1, which is 1, equals m, which is also 1, times x minus 0. Now, of course, that's not any of the choices. They've chosen to like put it in slope-intercept form. Basically, they just solved for y. So this is y minus 1 equals x, which means that y is equal to x plus 1. So it looks like that's b. Okay, AP 16. Okay, they give you a hint. I don't need the hint. The line tangent to the graph of the function passes through the point. Then f prime of 1 is... Okay, I see what to do. So here's the thing. Think about the tangent line, okay? The tangent line they're talking about is the tangent line at this location, at 1, 7, right? Therefore, the tangent line definitely goes through this point. But we also know that it goes through this point. That means we can find the slope of the tangent line because we have 2 points on the line. So you can do like, rise over 1, right? Like y2 minus y1 over x2 minus x1, that sort of thing, right? So the slope of this tangent line is, so y2, which is negative 2, minus y1, which is 7, over x2, which is negative 2, minus x1, which is 1. That's going to be the slope. So that's negative 9 over negative 3, which is just 3. So the slope of this tangent line is 3. Okay? Oh, right. By the way, where is this tangent line, right? This is the tangent line at x equals 1. So the slope of, so maybe I'll just say for emphasis, slope of the tangent line at x equals 1 is 3. Look, that just means f prime of 1 is 3. That's what that means. So f prime of 1 is 3. Okay, at the end. If f of x is then the value of the derivative f prime. Yeah, we don't really talk about derivatives of absolute value functions because in general, like they're not like they're not differentiable. Okay, like in general, at least at the basic absolute value function. If you think about what the basic absolute value function looks like, it's got a corner at 0, right? Like it's got a sharp, if I'm like y equals absolute x, looks like that. It's got a corner. It's differentiable here, like all along here and stuff, but it's not differentiable at 0, okay? And I would just think about this as saying, look, like what does this graph look like? Well, the minus 3 here moves the graph 3 units to the right, and the 2 here moves the graph 2 units up. Like, so the graph of this function just looks like this, but moved 3 units right and 2 units up. And then they ask you, what's the derivative of that function at x equals 3? Well, in this graph, the corner is at x equals 3, so it's not going to be differentiable there, right? I mean, of course, you don't have access to a calculator, but, right? You see what I mean? There's the corner at x equals 3. It's not differentiable there because it's got, so I think you should just think about what the graph of this thing looks like and then say, oh, there's a corner there. So it's non-existent. Sorry, that was AP 18. Yeah, so non-existent. AP 6. Which of the following statements is true? Okay, does it have a limit at x equals 2? Yes. Wait, maybe not. I have to check. So what they mean is, does the two-sided limit exist at 2? So you've got to check the left and right-hand limits, right? So if I approach 2 from the left, that means I'm not at 2, right? I'm not at 2, which means I'm using the first formula, because I'm not at 2. So I'd be looking at this limit, right? X squared minus 4 over x minus 2. If you factor the numerator and cancel common factors, that'll turn into x plus 2, and so you're going to get 4. Okay, so left-hand limit is 4. Well, what about the right-hand limit? Well, the thing is, like, if you're approaching 2 from the right, you're also not at 2, right? So you're still not at 2, so you're going to be using the same formula for the right-hand limit. So the right-hand limit is computed using exactly the same formula, which means it's going to come out to be exactly the same. It's going to be 4. See what I mean? So the left and right-hand limits are both 4, so 1 is true. It has a two-sided limit. Is f continuous at 2? Definitely not, because the value of the function at 2 is 1, which is not equal to 4, right? So it's not continuous there. 3, is it differentiable at 2? Definitely not, because differentiability requires continuity, right? If it's not continuous at 2, then it's certainly not differentiable either. So in fact, it's just 1, right? 1 only. So A. 76, the graph of the function is shown for which of the following values are... It's kind of an old one. One is f prime positive and increasing. Let me see. On this region, f prime is negative, right? So forget about that. On this region, f prime is positive, but I think it's decreasing because here the slope is maybe like 3, but here the slope is a little bit less, right? So the slope is sort of decreasing. And then on this region, f prime is like negative, certainly, right? And then here the slope is 0, right? So like right here, f prime is 0, and here f prime is so I would say at E, like I think at E only, right? F prime is positive, and it's increasing, right? Because like, you know, a little bit before E, the slope is maybe 2, and then after E, the slope is like 3, so I'd just say it's E. Okay. In the xy plane, the line x, sorry, I keep forgetting to say which problem I'm working on. So that was 76. 18 is what I'm doing now. In the xy plane, the line x plus y equals k, where k is a constant, is tangent to the graph of blah, blah, blah. What is the value of k? Okay, well, I mean, one thing I can say is this guy is I'll say a tangent line. It is a tangent line to, you know, to this function that I'll call f. Okay, it's a tangent line. Where is it the tangent line? They don't tell you. You don't know. Maybe it's a tangent line at 1, maybe it's a tangent line at 2. You don't know. But I think I can find out, because this is the equation of the tangent line. I can solve it for y and get it into slope-intercept form. That's y equals mx plus b. That coefficient right there on the x, that's the slope of this line, which is -1, right? So I can say the slope of this tangent line is -1, all right? So now, I don't know where this is the tangent line, right? But I know that the slope of this tangent line is -1. So wherever this is the tangent line, the derivative is -1 at that location, right? So I don't know where this tangent line is, but the slope of this tangent line is -1. That means that wherever this is the tangent line, the derivative of this function is -1 there, right? And that's the clue that I use to figure out where is this the tangent line, right? Because wherever it is, it's where the derivative is -1. So I'm going to figure out where is the derivative of -1, right? So there's the derivative. I set that equal to -1 and I solve. So I get 2x is equal to -4. So x is equal to -2. That's telling me that this guy is the tangent line at x equals -2, because that's where the derivative is -1. All right. So therefore, you know, this x plus y equals k is the equation of the tangent line at at -2. Okay, that's what I know. Cool. Now the thing is, this, like, the tangent line function, like this guy right here, that's a function, right? It's the tangent line. And the original guy right here, the quadratic, they have the same value at this location. They have the same value at that location, right? Like if you think about the graph of any function, you know, whatever it is, and then you think about the tangent line. Give me like 1 second here. Why are you mad? Oh, there we go. Yeah. If you think about any function and you think about the tangent line, like the point, like this point right here, okay, is always on both the curve and the tangent line. Like, in other words, wherever the tangent line has been drawn, the original function and the tangent line have the same value. They've got the same y coordinate at that moment. So, like, I already know that this is the tangent line at x equals -2, right? So, like, I know that the original function and the tangent line have the same value at -2. And that's what I'm going to use to find k, right? This function and this function have the same value at -2. Well, this function evaluated at -2 is opposite of -2 plus k. And that needs to match the value of this function at -2. So that's -2 squared plus 3 times -2 plus 1. So that's 4 plus k is equal to 4 minus 6 plus 1. I think the -5. Is that right? Is that one of the options? Nope, I screwed up somewhere. Where did I screw up? Probably this last step, honestly. No, that's not the problem. Oh, because opposite of -2 is not 4. Is not 4. That's just 2. That's just 2. So I've got 2 plus k equals -2 plus 1. So k is equal to, so that's -1, -3. Yeah, I think it's A. Cool. Okay, so AP 23 is this function. If this function is blah blah blah, f prime -1 is well, basically you need to make sure that the left and right slopes, like, well, for like, is this function differentiable at -1, right? Because if it's not, then f prime of -1 is definitely not existent at all. So let's just check that. Is it continuous at -1? If I plug in -1 to the left, I get -3 plus 5, which is 2. If I plug -1 into this guy, I also get 2. And then the function at yeah. So it's continuous at -1. Do the slopes match at -1? On the left, the slope is 3. On the right, the slope, I have to think about it. On the right, the derivative is -2x. But if I plug in -1, then I get -2 times -1, which is 2. Okay. So the slope on the right is +2, but the slope on the left is 3. That means the function's not differentiable at -1, so the derivative doesn't even exist there, so it's e. If the left and right slopes did match, like if they were both 3 or something, then the derivative would exist and it would just be 3. Okay. Enough be the what is the value of c plus d? Oh yeah, I mean, why do they ask you to find c plus d? Basically because multiple choice questions in the AP, they want to just have one part. So you're just going to find c and d like you usually do, and then add them together. Okay, so it's differentiable That means that the values of the original function have to match, so c times 1 plus d, sorry, it's at 2, right? So c times 2 plus d is equal to 2 squared minus c times 2. Let me clean that up. That's 2c plus d equals 4 minus 2c. So 4c plus d equals 4, okay. And then the derivatives have to match. The derivative on the left is c. The derivative on the right is 2x minus c. Those guys have to equal at 2. So c is equal to 2 times 2 minus c. So 2c is equal to 4. So c is equal to 2. And then if I go back to this guy and substitute, I find 4 times 2 plus d is equal to 4. So d is equal to negative 4. So therefore c plus d is 2 plus negative 4, just minus 4, which is negative 2. So I think B. 13. The graph of the function has a vertical, okay, and horizontal tangent, okay. So between negative 2 and 4, where is f not differentiable? 0, because the original function has discontinuity there, right? At 2, because it's a vertical tangent line. And that's it. I mean, of course, like the derivative would be undefined at 4 as well, because the tangent line's getting vertical there as well. But they're only asking you about x values strictly between negative 2 and 4. So like you don't care about 4. So yeah, so it's 0 and it's 2 only, right? Like there's nothing wrong with 3. The derivative is just 0 at 3. That's fine. It's not undefined. Again, there's nothing wrong with 1 either, right? Yeah. Okay. AP 23. The graph of f is which of the following? I mean, real fast. I just like to be like, where's the derivative 0, right? Where's the derivative 0? So it's 0 like right here. So I'm looking for a graph whose value is 0 at that location, right? So like could be A. Don't think it's B, right? Like the value's not 0 at that location. Could be C. Don't think it's B either, right? Like I want the derivative to be 0 right here, like just like a little bit past the origin, and it's not. I guess it could be E. So I think it's either A, C, or E, because all three of these have a value of 0, like at this location just to the right. Okay, well, like, what are things like at the beginning? At the beginning, the slope is quite flat, right? So, like, the derivative should sort of start at 0. I think that rules out E, you know what I mean? Like, the value here doesn't start at 0. So it's either A or C. If I go a little bit further, you know, the slope sort of starts at 0, but then, like, it's positive, right? The slope is positive here. That matches A, right? 0 to positive. So I think it's A. Oh, we're done. Oh, thank God. Okay, hope that was useful, guys.